Hello everybody, welcome to the lecture in downstream processing in biotechnology. This lecture we will continue on the crystallization process, and we will focus on the how to measure the solubility and what is the nucleation. As I talk to you, we have two kinetic of the crystallization. The first is nucleation and the second is crystal growth. For the crystal growth, you talk to it the next lecture, but for this lecture, I will focus on nucleation. And before we focus on the crystallization kinetic, we have to talk to you about this solubility measurement. The solubility measurement or the solubility is very important parameter, because if we would like to generate or create the supersaturation, we have to know first is the solubility. If the concentration is higher than solubility, we can obtain the crystal. If the concentration is lower than solubility, we cannot obtain the crystal. We have to adjust or disturb the solution. Maybe it's by cooling, crystallization, or evaporation, or add some solvent for the entire solvent crystallization. Okay, for this slide, we will talk about how to measure the solubility. The easy way for measure the solubility, we call it gravimetric method. Gravimetric method, that we measure at constant temperature or isothermal condition. Isothermal condition. For example, we have some vessel or some reactor. We put this in the water bath to control the temperature. In this, we have a mixer. The mixer can help to the dissolve of the solution. Okay, for this case, we use the gravimetric method. That means we add some solute in terms of solid in the solvent, and then you mix it until it reaches equilibrium. If we confirm that it reaches equilibrium or not, something that we until you solve, that's why you dissolve this with respect to time, and then you collect the solution. That's why we collect the solution or sampling the solution, and then you filter. You get solution, the clear solution and solid. The solution you have to measure the concentration, and then you plot between the concentration and time. And then you get the concentration will increase with time. For example, right, this time, this concentration at the start is 0, and it's called increase in heat until it reaches the constant. This means the concentration is reached equilibrium. That means if you add more this crystal, more solid, it cannot dissolve because we fix the temperature at constant. This is the gravimetric method. It's like gravimetric method. And also how to determine the solution. During the mixing, during the mixing, you sampling the solution by filter. You get the clear solution. And then you have to calculate how much amount of the solute in the solution. The easy way is maybe dry subtrant method. That means you have some vial, you have some solution, and then you try to evaporate the water or the solvent out, and then you remain only the solid. You can measure the amount of solid that remain in the solution. Then you can calculate in terms of mass, the volume of solution, mass per mass of solution. You can calculate by this technique. Or another technique by the polythermal method. Polythermal method means we calculate at not constant temperature. For this case, we use the crystal 16 or we use the turbidity measurement. At the first step, we prepare the solution, and then you stir and heat. After you start the heat, you measure the turbidity measurement, and also increase temperature. So you increase the temperature, increase the temperature. Okay, you measure the temperature and turbidity. If there is some solid in solution, we have some turbidity. If the all solid dissolve, that means there is no solid in the solution. The turbidity is clear point. We get the clear point. And then you can determine what the temperature at the clear point. At that point mean the solubility. At this point, the solubility. This is the technique to measure by polythermal. You increase temperature. And also during you increase temperature, you have to measure the turbidity. After you increase the temperature, solid will dissolve until all of solid dissolve. At that point is the solubility. At that point, you have to determine what temperature at the point that all solid dissolve. That all solid. So we call the solubility. Right. That is technique. You can crystallize that is technique. For this case, the heterotoxicity means transmissibility technology. If the 100 transmittant, that means there is no solid in the solution. All of the right can pass to the solution. Yes, I can pass to the solution. Like for the example, this is the transmittant increase because some solute dissolve in solvent and then it get 100 or 100 this transmittant. That's like 100 transmittant. This 100 transmittant, and this is the temperature. With the temperature increase, at this point, at this temperature is about 50 is the solubility of this. Right? At 50, and also at this is the temperature of the solubility, something like this. That's right. This because this line is the transmissibility or transmittant from 0, right? And it's increase the picture. This is 100% dissolve. We can calculate this is the temperature. And also we can use FBRM. FBRM focus beam reflection measurement. That's right, reflection measurement. And also you utilize the technique of turbidity. Okay, for this case, we measure the temperature. Okay, the first step is maybe decrease the temperature and then you increase temperature or heating. That's right. This is the FBRM measurement. Okay, after you heat the temperature, and FBM is drop rapidly to 0. Drop rapidly to 0. That is this point you can assign. It's 0 at this point. Okay, this temperature is the saturated or solubility. For this case, you prepare the amount, amount of solute and amount of solvent. Amount of solute and amount of solvent, and you can calculate concentration. And what is the saturated temperature? You can measure from this point, and also for this case, amount of solute, dissolved, and solvent. But you can calculate the temperature at saturated. You can calculate from this point. And it's different to the convective method. For convective method, you fix temperature. You calculate the concentration. For this case, you calculate the concentration. This concentration is the saturated at the constant temperature. It's different. It's the isothermal condition. This is the polythermal condition. Beside the valley temperature. Okay, the first kinetic of the crystallization, we call it nucleation. As I talked to you earlier, we have two kinetic. Nucleation is the generation of a new crystal, and crystal growth. Crystal growth is the crystal grow to a larger size. Okay, the first new kinetic is nucleation. As I show you in this slide, this is the molecule. At the start of the crystallization, some molecule move to contact its starter. Some molecule contact is move out until it reaches the critical cluster of the molecule. The critical cluster of it, a lot of molecule aggregate together until it reaches the solid form. This is the nucleation. This is nucleation. Nucleation in the generate of new crystal. There is no crystallization. There is only molecule vibration movement of molecule. That's why some molecule move together, some molecule move out like this until a number of molecules move together and you list a critical number of molecules, and then we convert to the crystal or solid form. We call this nucleation. Right. We have at least two nucleation. That's why with primary nucleation and secondary nucleation. Primary nucleation means the crystal nucleate from the clear solution. The clear solution. This is separate into homogeneous and heterogeneous. homogeneous solution is the new crystal formed a very high supersaturation. That crystal can form from the clear solution by spontaneously by crystallization. But for heterogeneous solution, it also occur at high supersaturation, but in the solution, it may be foreign particle. It may be some dust. It may be like the surface of the reactor, surface of the crystallizer. It may be some roughness. Okay, it may be induced by outer surface, reduced by outer surface. This is the primary nucleation. And the secondary nucleation, the crystal cannot generate from the clear solution. But for this, the crystal generate from the seed of crystal. That means we assume the solution already have like the crystal. For secondary nucleation, it may be the breakage of the crystal from one crystal, breakage in two, in three, in four crystal. Right, this for example. I will talk to you in detail for that. Right. And also we back to the solubility curve. The solubility curve we have right there. This is under saturated zone. This is the saturated zone. This is the metastable zone. This is the lower concentration, but also it's supersaturation, but it cannot generate it, but only the growth. And this is the zone of the heterogeneous nucleation. And above this is the homogeneous nucleation. As I talked to you, homogeneous is induced the crystal by from the clear solution. But for heterogeneous, it may be induced by the foreign particle or by the large surface of crystallizer or by dust. If there are some impurity in the solution at higher than metastable zone, is lower than the primary homogeneous. This is the heterogeneous homogeneous. Okay. For this case, the formation of new crystal is crystal form a liquid or more fat phase is called a nucleation. I talked to you what is primary nucleation. The primary nucleation process is occur in a previous crystal free solution. That means the clear solution, no crystal, no foreign particle. Okay, for clear solution. Okay, it's separate in homogeneous and heterogeneous. Homogeneous means the clear solution crystal can occur spontaneously in clear solution with free of impurity. But homogeneous, the crystal generate from clear solution also, but there are some represent of inert foreign particle, such as that it may be due to the lackness of crystallizer, it may be some impurity in the solution, but also it's higher solution, it's supersaturation, higher than metastable. Right. Mostly we can express the nucleation by the classical nucleation theory. The classical nucleation theory, we assume the system is stationary. The crystallizer is fixed. There is no mixing. Then we have only the clear solution at stationary, and then we induce the crystallization by spontaneously. We can express in terms of J is the nucleation rate. Nucleation rate means number of crystal per volume of solution. It's a function of supersaturation ratio. 8 is the action concentration divided by saturated concentration or solubility. A function of constant A and B. Constant A and B, like this equation. Or you can convert this in terms of logarithm. If you know the concentration or you know the supersaturation and you measure the nucleation rate, you can determine A and B. Like you can plot this term and 1 over natural log square S, you can determine A and B for this case. But B is only expressed in terms of the thermodynamic property, right? For the spherical crystal, you can assume B is 16 pi V0 square gamma power 3 kT. That's why V is the molar volume of the crystal. Gamma is the interfacial energy, and K is Belmont constant for this case. As in mostly in industrial application, we can represent the nucleation rate as a function of driving force or supersaturated solution. We call this empirical polar model. That's right. Nucleation is the B is the birth rate of new crystal. It's a function of concentration in terms of delta C, C minus C star power B. Kn and B you can estimate from the experimental data. Kn is the nucleation rate constant, with Kn and B depend on physical property of the system, like for temperature, impurity include, condition like agitation intensity, agitation speed, concentration of crystal in the suspension, for example. Right. Okay. For the next nucleation, we separate in primary nucleation and secondary nucleation. For secondary nucleation, there are at least 5 principal mechanisms for secondary nucleation. The first principle is contact nuclei. Contact nuclei mean in the solution we have right supersaturated solution and crystal. And crystal. For this case, if the crystallization is proceed, solute in the liquid phase move to the solid phase by mass transfer. And then it's attached to the surface of the crystal. And also for this case, we have mixing. There are some contact between crystal and crystal, crystal and vessel, crystal and impeller. And for this case, the adsorbed layer or the attached layer of solute at the surface of crystal is maybe moved out. That's right. It may be moved out by the crystal contact, crystal vessel contact, or crystal impeller contact. That's right. The amount of solute attached to the surface is moved out, and then it's also form a crystal. It's a new crystal. And for the next mechanism is shear nucleation. Shear nucleation is also right the same as the first one. The solute that attached to the surface of the crystal. And also for this case, we have the fluid flow by mixing. Some fluid shear, that's right, fluid shear. It's maybe the adsorbed layer can move out by fluid shear to form the new crystal. And the third one is fracture nucleation. Fracture nucleation means the breakage of the crystal by the mechanism of crystal contact, crystal vessel contact, crystal wall contact, crystal impeller contact. After its contact or collision, that's right, a collision, it may be break into 2 crystal, 3 crystal, or something. That's right, or something with the fracture nucleation. And another is attrition nucleation. Attrition nucleation is mean the attrition of fragment of like a crystal caused by contact, similar in like crystal contact, crystal vessel wall contact, crystal impeller contact. But for this case, in the form of very small crystal. The third one is a big crystal, break to the 1, break 2 into 2 into 3. But for number 4, there are some contact and also attrition. The fragment of small crystal can break. That's right. And the last one, needle breaching. Needle breaching, this result from the removal of dendritic fragment from a larger crystal. Because some crystal is not like cubic, it's not sphere. It's maybe some the branch, it may be some dendritic. That's right. For this case, there are some contact between crystal vessel, wall, crystal impeller, and the dendritic is fragment of breakage from the large crystal. And also this is the 5 mechanism of the secondary nucleation. And mostly in the secondary nucleation, we can express the secondary nucleation in terms of the empirical model, right? It's a burst rate is a function of Kn sigma power A T power B omega power C MT power D. Kn is the nucleation rate parameter, right? Nucleation rate, but it's the same. Like this is the nucleation rate constant. And term A, B, C, D is constant. We can estimate from the experimental data. Sigma is the relative supersaturation. S minus 1. S is the supersaturation ratio. C divided by C star. T is absolute temperature. Omega is the agitation speed. That's right, lambda per minute, lambda per second, something like this. MT is the suspension density. It may be gram of crystal per gram of suspension. The suspension means mixture of solid and liquid. Solid and liquid. This is the most common used in industrial crystallization. You can express the solute concentration, temperature, aggregation speed, suspension density. That's right, suspension density. You can calculate this. You can correlate this from the experimental data. Okay, how to measure the nucleation rate? There are many ways to measure the nucleation rate, but quite difficult. The nucleation rate measurement mostly we determine the number of crystals that occur during the crystallization. For this case, we use the microscope to directly to count the number of crystals. Okay, for example, we start at T0. T0 is the undersaturated solution. And then you cool the temperature to Tsat. Tsat means it is saturated at this concentration. At this concentration. And then you reduce the temperature far to 0.1 is T1. At T1, the concentration is also constant, but at this temperature, the concentration is supersaturation. This is the saturation at T1. And this is the supersaturation. And it is higher than metastable zone. That's right, it's higher than metastable zone. For this case, it can induce the primary nucleation or spontaneous nucleation. Okay, for this case, after you reduce to 0.1, okay, from this you can get T1 reduce to T0 reduce to T1, and then the keep for time interval for delta T1. Delta T1, the time for nucleation. But in the microscope, if the crystal is very, very small, is smaller than micron, it's difficult to contact by microscope. That means you have to increase temperature rapidly. And then at delta T1, you increase the temperature rapidly. For this case, the temperature is reduced to 0.2. At 0.2, you can see that this point, the new crystal cannot occur. The new crystal cannot occur. For this case, only the crystal can grow to the larger size because it is the metastable zone with only the crystal growth. For this case, the objective, we would like to grow the crystal from nucleation from a very small size to be a larger size that can be observed by the microscope. That can be observed by microscope. That's like this for the undersaturated solution. And then you reduce the temperature until it T1. This is the supersaturated solution. And this is the time for nucleation. Because mostly the nucleation crystal is quite very small size. And then you have increased the temperature is rapidly to T2. T2 is the growth zone of growth crystal, no nucleation. That means for it you can observe by eye or can observe by microscope. For this case, is the equipment. You have the microscope, you have the crystallization cell, you have the temperature control water bath, right? And you have the camera to connect with the computer. You can observe or take the picture of the crystal like this. For this, you can count the number, that's like the number of crystal after the growth process, right? And then you plot the number of crystal. That's the number of crystal you count for this. This is at supersaturated 1.36 at time 10, time 15, time 40, time 20. You plot number of crystal with respect with time. For example, like this. And then you fit the equation at like n is a function of time at this equation. And then you can calculate nucleation rate. The nucleation rate is the nucleation at the earlier state at t equal to 0. It's the slope at initial state. That's like for the nucleation. Okay. For this case, you can diff n with respect to t. You get ABE power minus BT. And therefore, mostly the crystal we calculate at delta t approach 0. You substitute t equal to 0. You get AB. Right? You get AB. And then you can calculate nucleation rate by AB divided by volume because the nucleation is the number of crystal occur at initial state divided by the volume of solution. And then you can plot like the absolute supercent or C is a function of nucleation rate like this. And also for this, you can estimate, right? You can plot between the primary nucleation. You can plot between log J divided by supersaturation and 1 over log square x, and then you get the intercept at log a, and slope is minus b. So you can calculate a and b. B is also you can calculate the interfacial energy. Yes, you can calculate interfacial energy for that case. Low interfacial energy indicate higher nucleation rate. Higher nucleation, that means it's easy to nucleate. Yes, it's easy to nucleate. And also you can measure the nucleation rate by FBIM. Previously we determined by the microscope, but the next step we determine by the FBIM, because FBIM also count the number of crystal. The technique is the same, but for this case we have no like the time for growth, the time for something, because the FBIM is determine the number directly. For this case we have like the crystallizer, control water bath, control the temperature. By the jacket we have the mixer by magnetic bar, and then we have the FBIM probe. Okay. For the FBIM probe, it count the number of crystal with respect to time. For example, we plot the time and number of crystal. For this case, the number of crystal is plot in terms of per volume already. Okay. We have plot like this, plot like this. That means the nucleation rate is calculated from the initial state, like this technique. We form the initial state at delta t approach 0. This means the nucleation at the initial state. That means you can determine the slope at initially. This is the slope of the nucleus crystal. Aside. By slope of this, you get number of crystal per volume per time, nucleation rate. Aside this nucleation rate. And then you get the nucleation rate with the supersaturation. At initial supersaturation, we get a different nucleation rate because the nucleation is mostly is function of supersaturation. But for this case, we use the entire solvent crystallization, and also the volume of ethanol is different. Like this. And then you can pass log j over s and 1 over log square s to determine a and b parameter. And you get the a and b parameter, and then you can calculate interfacial energy. Interfacial energy. For this case, the interfacial energy at ethanol is higher than methanol, acetone, and acetone. That means the ethanol is difficult to nucleate when compared to the methanol, acetone, and acetone. For this case, acetone can induce the nucleation is better, is the higher nucleation rate. Higher nucleation rate for that case. For example, this the technique that I show you how to measure the nucleation rate. We can measure the nucleation directly by the equipment like microscope or ABIM. That's right. For the crystallization kinetic, we have at least two terms, two kinetic, nucleation and growth. For this, we talk about the nucleation, and for the next lecture, I will talk about the growth. That's right. Okay. For this lecture, I will stop now, and thank for your attention.